In the cold dark between stars, a young sun forms inside a thin, spinning disk of gas and dust. The disk looks quiet, but it is full of slow collisions, gentle sticking, and steady growth. Dust grains gather into clumps. Clumps become larger bodies. Rings and gaps appear as gravity begins to organize the flow. Over time, the disk starts to separate into zones where rock, ice, and gas follow different rules. Some material falls inward, some drifts outward. Some collects into the first planetary cores that will eventually shape everything around them. This documentary follows that calm process from the widest disk structures down to the hidden places where planets take form. It stays with the physics of dust, gas, gravity, and time, showing how worlds begin without drama, only patience and motion. If this kind of slow, science-grounded space storytelling helps with sleep, focus, or quiet study, please like the video and subscribe to the channel for more calm documentaries about the universe and the worlds inside it. Across the galaxy, star formation begins far from any single sun, in regions where the space between stars is faintly textured. The raw material is gas, mostly hydrogen and helium, mixed with a small fraction of heavier elements carried as atoms, molecules, and solid grains. This mixture gathers in giant molecular clouds, cold reservoirs that drift through spiral arms and quieter interarm space. Their outlines are irregular, shaped by past supernova shocks, stellar winds, and the slow shear of galactic rotation. From a distance, these clouds appear as dark lanes against starlight because dust grains scatter and absorb visible light more effectively than the surrounding diffuse gas. The temperature in much of this material stays low by cosmic standards, often only a few tens of degrees above absolute zero. Cold gas moves slowly, and its sound speed is small, so gentle compressions can create long-lived density enhancements. The clouds are not still. Turbulence stirs them on many scales, driven by expanding bubbles from massive stars, by cloud interactions, and by continual energy input from the broader interstellar medium. The result is a landscape of eddies and converging flows where density varies greatly. In the most rarefied parts, atoms and molecules drift with wide separations. In denser pockets, collisions become frequent enough for chemistry to proceed, building molecules such as carbon monoxide and water, and allowing the gas to cool by emitting radiation at specific wavelengths. Dust is the quiet partner in this process. Each grain is small, often comparable in size to smoke particles, and made of silicates, carbon-rich material, and icy coatings in the coldest regions. Though dust contributes only a small share of the mass, it dominates the interaction with starlight and provides surfaces where atoms can meet and react. Hydrogen molecules form efficiently on grain surfaces, turning diffuse atomic gas into molecular gas, the state in which clouds become more shielded and better able to stay cold. Dust also acts as a ledger of earlier history. The elements that build these grains are forged in stars and spread by winds and explosions, then mixed into new clouds. Within the broad expanse of a molecular cloud, external radiation shapes conditions from the outside. Ultraviolet light can ionize and heat exposed edges, creating bright rims and eroding surfaces into pillars and globules. Deeper inside, dust and molecules provide shielding. Starlight weakens, and the chemistry shifts toward forms that survive in darkness. Cosmic rays penetrate more deeply than light and maintain a low level of ionization even in well-shielded regions. This ionization ties parts of the gas to magnetic fields. Magnetic fields, though weak in absolute terms, influence motion in gas that is thin and electrically responsive. They can resist collapse, guide flows, and store energy that turbulence can tap and rearrange. Gravity is present everywhere, but it competes with pressure, turbulence, and magnetic support. A molecular cloud can persist for millions of years without turning all of its mass into stars because much of it remains unbound or only marginally bound. Large-scale motions can disperse a region before it collapses. Where collapse does begin, it often starts where converging flows raise density, where cooling remains efficient, and where support mechanisms fail to keep pace with increasing weight. Collapse rarely proceeds as a simple, spherical inward fall. The cloud fragments, filaments appear, long threads where gas collects along shocks and magnetic alignments. Along these filaments, knots form, and within knots, smaller condensations arise. The outer environment sets initial conditions for any future disk and any future planet. The fraction of matter in elements heavier than helium determines how much solid material is available to become grains and larger bodies. The local radiation field affects how much of the cloud stays molecular and how much becomes heated and dispersed. Magnetic fields influence how angular momentum is later transported once a disk exists. While turbulence affects the range of core masses and the likelihood of forming clustered groups, in some regions the birth setting becomes crowded and dynamic. Massive stars, if they form, influence their surroundings quickly. Their radiation can carve cavities and drive ionized fronts that compress neighboring gas, while stripping it at the same time. Strong ultraviolet fields can erode young disks from the outside, and close stellar encounters in dense groups can truncate disks and alter orbits. In quieter regions, low-mass star formation proceeds with less external disruption, allowing disks to retain more mass and survive longer. Even before any star shines, the gas carries motions inherited from turbulence and galactic rotation. These motions include angular momentum, a measure of rotation that later resists direct infall. On large scales, this angular momentum is modest, but as collapse concentrates material, this same angular momentum becomes dynamically important. It is stored in the slow spin of a forming core, and later appears in the disk that feeds the central protostar. The distribution of angular momentum in the parent cloud is uneven, shaped by shocks and by magnetic braking, and this unevenness contributes to the variety of disk sizes and orientations seen in young systems. The chemistry of the outer cloud leaves signatures that persist inward. In cold, shielded regions, molecules freeze onto grains, forming icy mantles that include water, carbon dioxide, methane, ammonia, and more complex organics. In slightly warmer or more exposed regions, some of these ices cannot survive and remain in the gas. The balance between frozen and gaseous forms determines what is carried inward as solids and what is transported as gas. Observations indicate that organic building blocks can form early in these environments, though it remains uncertain how much survives later heating unchanged and how much is rebuilt inside disks. At the wider scale, planet birth begins as a slow rearrangement of interstellar matter. Gas and dust drift, cool, and mix. Light from nearby stars sculpt surfaces while darkness preserves cold interiors. Magnetic fields thread the scene, and turbulence keeps it in motion. Gravity waits within every overdensity, ready to take advantage of any region that becomes heavy enough to fall inward. This outer setting determines how much material remains available, how it is conditioned by radiation and chemistry, and how the first steps toward a star and its surrounding disk become possible. Within the broad molecular cloud, the inward path leads toward regions where the gas becomes denser and more self-contained. These are the dense cores, compact concentrations that stand out from their surroundings not by sharp edges, but by a steady rise in column density. In maps made with far infrared and sub-millimeter light, they appear as cold, dark lumps against warmer backgrounds because their dust emits faintly at long wavelengths while absorbing more energetic radiation. In spectral lines of molecules that survive in cold gas, their internal motions become measurable, revealing whether a core is supported by turbulence, rotating, or beginning to collapse. A dense core forms where converging flows have piled up material, where a filament has gathered enough mass per unit length to become unstable, or where local turbulence has created a long-lived compression. Gravity contributes at every stage, but the key change is that the core becomes more gravitationally bound than the surrounding cloud. In the outer parts of the cloud, turbulent motions and magnetic support often dominate. In the core, gravity grows stronger because density is higher, and the free-fall time, the time a region would take to collapse if nothing opposed it, becomes shorter. The gas remains cold at first, and because it cools efficiently, pressure does not rise quickly enough to halt the gathering. The core is not a pure ball of gas. Dust grains are interspersed throughout, and their temperature tracks the balance between external heating and internal shielding. Near the core's outer layers, faint starlight can still warm the grains slightly. Deeper in, the grains cool toward a lower equilibrium. This gradient matters because the rate of many chemical reactions and the stability of icy mantles depend on temperature. In the coldest parts, many molecules freeze out onto grain surfaces. Carbon monoxide, a common tracer of molecular gas, can become depleted from the gas phase as it sticks to dust. As this happens, other ions and molecules become better tracers of the densest interior. The chemical makeup becomes layered, like a quiet record of exposure and depth. Magnetic fields thread the core. Because the gas is weakly ionized, it is not fully free to slip past magnetic field lines. Instead, neutral particles collide with ions that are tied to the field, creating a partial coupling. This coupling can slow collapse by providing magnetic pressure and tension. Over time, the neutrals can drift relative to the field in a process called ambipolar diffusion, gradually reducing magnetic support in the densest parts. Observations indicate that magnetic fields can be significant in many cores, but it remains uncertain how often they dominate over turbulence and how their importance varies across environments. Turbulence inside the core tends to be less violent than in the larger cloud, but it does not disappear. Spectral line widths show that some cores contain subsonic or mildly supersonic motions, depending on the region. These motions can provide temporary support and can also seed asymmetries that later guide fragmentation. A core can remain starless for a time, appearing as a cold condensation without an embedded luminous object. During this stage, it can slowly contract, or it can hover near stability, buffeted by its surroundings. The boundary between a stable starless core and a collapsing core is not always sharp. Some cores show inward motions in their line profiles, indicating contraction. Others show more random motions. The transition depends on the balance of gravity, pressure, magnetic fields, and turbulence, and on whether external compressions continue to feed mass inward. As collapse begins in earnest, the density rises toward the center. Inward moving material accelerates under gravity, but because the gas can still radiate away energy, the collapse remains close to isothermal, meaning the temperature stays roughly constant over a wide range of densities. This is a crucial phase because a constant temperature keeps pressure from rising too quickly, allowing the central density to increase dramatically. The core becomes more centrally peaked, and the velocity field begins to show systematic infall, though not necessarily in perfect symmetry. Small initial rotations become more apparent as the radius shrinks, because angular momentum is conserved. The core's spin may be slight, but as the collapse concentrates matter, the same angular momentum implies faster rotation closer in. The distribution of angular momentum inside a core is shaped by earlier turbulence and by magnetic braking, the process by which magnetic fields can transport angular momentum outward. If the coupling is strong, magnetic braking can reduce the spin of the inner collapsing material, potentially affecting the size of any future disk. If the coupling is weaker, more angular momentum remains in the inner regions. Observations show a range of core rotation rates and a range of disk sizes in young systems, suggesting that the efficiency of angular momentum removal varies. It remains uncertain how much of this variation is due to environmental differences and how much is due to the chaotic nature of turbulent initial conditions. At the same time, the core is rarely isolated. It sits within a filament that can continue to feed it, or it may be embedded in a small clump where multiple cores form together. In such cases, competition for mass and gravitational interactions can influence the final outcome. A core that continues to accrete from its surroundings can grow more massive and potentially form a higher mass star. A core that is cut off by feedback or by the dispersal of its filament may form a lower mass star. The mass that ends in the star is only a fraction of the core's initial mass, because outflows and radiation later remove material. Still, the core's structure and mass distribution set the starting point for that later partition. Even in the dense interior, chemical activity continues quietly. On dust grains, atoms and simple molecules migrate and react, producing more complex species. Some of these products can be released back into the gas by non-thermal processes such as cosmic ray impacts, keeping a faint gas phase chemistry alive in cold conditions. This chemistry matters later because it sets the inventory of volatiles that enter the disk. Water, carbon-bearing molecules, and nitrogen compounds can be stored in ices at this stage. Observations indicate that many of the building blocks relevant to later planetary atmospheres and surfaces are present early, though it remains uncertain how the later heating and mixing inside disks transforms this inherited chemistry. The core's collapse continues inward, becoming more focused and faster at smaller radii, yet it remains quiet in the sense that light is still largely absent. The energy released by infall is radiated away efficiently by dust and molecules. The scene is one of dark matter becoming denser, of a cold region tightening around a forming center. In this inward path, the core becomes the immediate parent environment of the protoplanetary disk. Its rotation, magnetization, and chemical layering shape what material can settle into orbit rather than falling directly onto the central object. By the end of this region, the collapse is well underway, and the central density is high enough that the next inward layer begins to behave differently, shifting from a cold, contracting core toward a newborn central object and the first stable rotating structures around it. As the inward journey continues, the collapsing core reaches a point where rotation becomes impossible to ignore. Even a small initial spin changes the geometry of infall once the material draws close enough to the center. Gas that falls straight inward can lose its orbital motion only if angular momentum is removed by forces such as magnetic stresses or gravitational torques. Where that removal is incomplete, the inward-moving gas begins to miss the center. It swings around it, creating a flattened flow that settles into orbit. This is the earliest outline of a disk, a structure born not from a deliberate shape, but from the simple rule that rotating material resists being forced into the smallest radius. The collapse remains largely cold at first, but density increases. In the central region, the gas eventually becomes opaque enough that radiation escapes less efficiently. cooling slows, and a small central object forms that is supported temporarily by pressure rather than by ongoing free fall. This object is sometimes described as a first hydrostatic core, a short-lived stage where the inward flow piles up and heats locally. Its lifetime depends on mass and rotation, and it is difficult to observe directly because it is deeply embedded and faint. It marks a boundary between purely isothermal collapse and the beginnings of a more complex central structure, where heating and radiation gradually begin to matter. Around this growing center, the disk emerges as a rotating flattened region. It forms first as a dense inner plane where gas streams converge. The disk is not immediately smooth. Infall continues from above and below the midplane, arriving along curved trajectories shaped by the core's rotation and magnetic fields. Shocks occur where incoming material strikes the disk surface, converting kinetic energy into heat and briefly warming localized zones. Because the system is still buried in the parent core, the disk is surrounded by an envelope of infalling gas. This envelope feeds the disk and the central protostar, and it also absorbs and reprocesses radiation, keeping the early system hidden from view at visible wavelengths. Angular momentum governs the disk's shape and evolution. The material at larger radii carries more angular momentum per unit mass than material close to the center, so it settles farther out. Over time, the disk can spread outward as angular momentum is transported. At the same time, mass moves inward, feeding the central protostar. This inward flow requires a mechanism to carry angular momentum outward. Otherwise, the gas would remain stuck in orbit. Several processes can contribute. Turbulence can act like an effective viscosity, allowing neighboring rings of gas to exchange angular momentum. Magnetic fields can link different radii and transfer angular momentum through stresses. Disk winds can carry angular momentum away in outflowing gas. In the embedded phase, gravitational instabilities can also redistribute angular momentum if the disk becomes massive enough relative to the central object. The efficiency of these processes depends on conditions. Ionization is low in much of the disk and envelope, which weakens magnetic coupling in some regions. Cosmic rays and X-rays can ionize surface layers, while dense midplane regions can remain weakly ionized. This layering affects whether the gas can participate fully in magnetically driven turbulence. Observations and theory indicate that disks can have zones where magnetic effects are strong and zones where they are muted, but it remains uncertain how these zones evolve over time and how they influence planet formation pathways. Rotation also shapes how matter fragments. If the collapsing core has enough angular momentum and enough mass, it may form multiple condensations rather than a single central object. These condensations can become a binary or multiple star system, each with its own disk or with a shared circumbinary disk. Fragmentation can occur in the core before a well-defined disk forms, or it can occur within a massive disk later. In the embedded phase, fragmentation is influenced by how quickly the gas can cool. If cooling is rapid, gravitationally unstable regions can collapse into bound objects. If cooling is slower, instabilities may instead create spiral density waves that transport angular momentum without fragmenting. Observations indicate that both single and multiple systems emerge from similar cloud environments, suggesting that small differences in initial conditions can lead to different outcomes. It remains uncertain how often disk fragmentation contributes to planet-sized bodies versus producing stellar companions. Within the forming disk, temperature and density vary strongly with radius and height. Close to the center, the disk heats by accretion and by radiation from the forming protostar. Farther out, it remains cooler and more influenced by the envelope and the ambient cloud. Vertically, The disk is densest at the midplane and more rarefied above, creating a layered structure. In this early stage, however, the disk's vertical structure is constantly disturbed by infall. Streams from the envelope land on its surface, compressing and stirring the upper layers. The disk can therefore be thick and dynamic, not yet the relatively settled structure often imagined in later, clearer stages. Dust follows the gas but begins to show subtle differences. Small grains are well coupled to gas and remain suspended, carried by turbulence and infell. Larger grains begin to feel gravity more strongly and may settle toward the midplane once turbulence allows. In the embedded phase, the time available for significant dust growth is limited, yet the conditions for sticking and coagulation already exist. Dust grains collide gently in the densest regions, sometimes sticking through surface forces and icy coatings. Where collisions become faster, grains can fragment or bounce. The earliest disk therefore contains a spectrum of grain sizes inherited from the cloud and modestly altered by local processing. The direction of inward motion changes in this region. In the outer core, material moves mostly inward. Here, it divides into two main pathways, a direct fall into the center, where angular momentum is low, and a settling into orbit where angular momentum is higher. The disk acts as a sorting device, separating material by its ability to circularize. This sorting also affects chemistry. Material that falls close to the center experiences higher temperatures and can lose ices, releasing molecules into gas. Material that settles farther out remains cold and preserves ices. Because infall continues over time, the disk can receive successive layers of material with different histories of temperature and exposure, building chemical gradients from the start. Outflows begin to appear as a consequence of rotation and magnetic fields. As material accretes inward, some of it is diverted into jets and winds launched from near the disk and the protostar. These outflows carve cavities in the envelope, creating channels through which radiation can escape more easily. The presence of outflows is one of the most visible signs that a protostar is forming, even when the system remains hidden in dust. Outflows also remove mass and angular momentum, influencing how much material remains available for disk evolution and, later, planet formation. The combined picture is one of a rotating collapse that cannot remain spherical. The inward flow flattens, forms a disk, and begins to organize itself into a system where mass moves inward and angular momentum moves outward. The disk is young, embedded, and fed from above, and its structure is still being built even as it begins to regulate further accretion. In this region, the basic architecture has established a central forming star surrounded by a rotating disk, still wrapped in an envelope, with magnetic fields and gravity sharing the task of shaping motion. The inward path now approaches the central source of heat and light that will increasingly define conditions in the disk. Moving inward, the forming system reaches the point where the central object becomes more than a pressure-supported condensation. The protostar grows as gas accretes onto it through the inner disk and through flows that connect disk and envelope. Its interior compresses under its own weight. Gravitational energy turns into heat. The earliest luminosity is not produced by stable nuclear fusion in the core, but by the energy released as material falls into deeper gravitational potential and settles onto the protostar. This accretion luminosity can dominate the energy budget during much of the embedded phase, and it sets the earliest thermal environment for the inner disk. The protostar remains surrounded by dusty gas that absorbs and re-emits much of its radiation. At visible wavelengths it is still hidden, but at infrared and longer wavelengths the warmed dust becomes a beacon. The light that escapes does not travel through empty space. It propagates through the cavities carved by outflows, strikes envelope walls, and is scattered or absorbed by dust grains. The emerging radiation field is therefore highly shaped by geometry. Some directions offer clearer paths through outflow cavities, while other directions remain buried behind thick columns of dust. The result is an environment where heating is uneven, with warm zones along cavity walls and colder zones deeper in the envelope and outer disk. As the protostar accretes, its mass increases and its radius remains relatively large compared to a main sequence star of similar mass. The surface is hot enough to emit strongly in the infrared. The protostar's temperature and luminosity evolve with time, depending on accretion rate and internal structure. Accretion is not always steady. Observations of young stars and theoretical models indicate that accretion can be episodic, with bursts where the rate increases markedly. During a burst, the protostar brightens, and the increased luminosity can heat the disk to larger radii than usual, temporarily altering chemistry and the distribution of ices. It remains uncertain how common strong bursts are, and how much they contribute to the final chemical and structural makeup of planetary systems. But there is strong evidence that variability is a real feature of early accretion. The inner disk now becomes a key mediator between envelope and star. Gas arriving from the envelope lands on the disk at radii set by angular momentum. From there, it must move inward. The rate at which it does so depends on the transport of angular momentum, which can be driven by turbulence, by magnetic stresses, and by gravitational torques. In the inner regions, temperatures rise, and ionization can become higher due to thermal ionization of some elements and due to radiation from the protostar. This increased ionization can strengthen magnetic coupling, allowing magnetically driven turbulence and winds to act more efficiently. The inner disk is therefore often more active in transporting angular momentum than the outer disk, though the details remain an area of ongoing research. Heating in the disk comes from several sources. First, viscous dissipation, the conversion of orbital shear into heat through turbulent motions, warms the midplane, especially where accretion rates are high. Second, irradiation from the protostar warms the disk surface, creating a vertical temperature gradient. Third, shocks from infalling material can add localized heating. These combined effects produce layered thermal structure. The surface can be warm and directly exposed to radiation, while the midplane can be cooler or warmer depending on how strongly accretion heats it from within. Dust opacity plays a central role because it determines how radiation is absorbed and re-radiated. Grain size and composition affect opacity, so as dust evolves, the disk's ability to trap heat evolves too. Chemistry responds quickly to the changing temperature field. In colder regions, molecules stay frozen onto grains. In warmer regions, they evaporate into the gas. The boundary where a specific volatile transitions between solid and gas is often described as a snow line. In this region of the inward path, the earlier snow lines appear and can shift with protostellar luminosity. Water, carbon dioxide, carbon monoxide, and other species each have their own characteristic temperatures for freezing and evaporation, so their snow lines lie at different radii. When the protostar brightens, snow lines move outward. When it dims, they move inward. This motion alters what solids carry which volatiles and can influence the building blocks available for future planets. Observations indicate that snow lines exist and can be inferred in some systems, but it remains uncertain how sharply defined they are in all disks and how turbulent mixing blurs their boundaries. Dust grains themselves are altered by heating. Near the protostar, icy mantles cannot survive, leaving bare refractory grains. At higher temperatures, some solids can evaporate, and in cooler zones farther out they can recondense. This cycle can change grain sizes and compositions. It can also concentrate certain materials at specific radii if vapor diffuses outward and condenses just beyond a snowline. Such processes are considered important for the distribution of solids in disks, yet their efficiency depends on transport rates and on how quickly grains grow and drift. The protostar also begins to influence its environment through energetic radiation and particles. Young stars can produce strong magnetic activity and emit X-rays. These X-rays penetrate disk surface layers, ionizing gas and driving chemical reactions that do not occur in cold, neutral regions. Ultraviolet radiation, when it escapes through cavities, can dissociate molecules and heat gas in exposed surfaces. The interplay of shielding by dust, geometry of cavities, and variability of emission determines how deeply these energetic photons reach. Observations indicate that surface layers of disks are chemically active and can be warmer than the midplane, but it remains uncertain how these layers exchange material with deeper regions over long timescales. Outflows continue as a defining feature. Jets launched from near the star-disk interface carry away angular momentum and mass. They maintain cavities and can shock surrounding gas, creating knots of emission. The presence of outflows means that accretion onto the star is linked to mass loss. The system is not simply accumulating material, it is also expelling it. This balance affects how much disk mass remains to form planets and how long the disk can persist in its gas-rich state. As the protostar grows, the surrounding envelope gradually thins. Some of its mass is accreted, some is swept away by outflows, and some is dispersed by radiation. This central source becomes a stronger and more stable determinant of conditions. The region now is one where heat and light are no longer negligible. The disk is still embedded, but the inner disk and protostar begin to imprint their influence outward. Temperature gradients sharpen, chemical transitions become mobile, and the system becomes observable through the infrared glow of warmed dust. In this inward step, the forming star establishes itself as the energetic engine that will set the stage for the disk's evolution, while still relying on the disk as the conduit that delivers mass inward and removes angular momentum outward. Moving farther inward through the system, attention settles on the disk itself, beginning with its outer reaches where conditions remain most similar to the original cold cloud. The outer disk extends to tens or even hundreds of astronomical units from the central protostar, depending on the system's angular momentum history and interactions with its surroundings. In these far regions, the disk is thin and faint, a broad rotating sheet of gas and dust that fades gradually into the remnant envelope and then into the surrounding interstellar medium. The light from the protostar arrives diluted, and the temperatures remain low enough that ices persist on grain surfaces. The outer disk is defined by a layered structure. Along the midplane, the density is highest. Gas pressure supports the disk vertically against the star's gravity, giving it a finite thickness that increases with radius where the star's pull is weaker and where temperatures can be slightly higher in the surface layers. Above the midplane is a more rarefied atmosphere of gas and small grains. This surface is exposed to radiation from the protostar and to the background ultraviolet field of the region. The surface absorbs energy and can become warmer than the midplane, even when the overall disk is cold. The result is a vertical temperature gradient, with the midplane acting as a cold interior and the surface acting as a warmer skin. The outer disk is also where much of the disk's mass can reside, especially in gas. Hydrogen and helium dominate, with trace molecules and atoms providing most of the observable spectral signatures. Dust grains contribute a smaller fraction of the mass but dominate opacity. In the outer disk, dust grains are often still small enough to remain well mixed with gas in the surface layers, while larger grains, if present, tend to settle closer to the midplane. Observations of disks at long wavelengths indicate that grains can grow beyond interstellar sizes early, even while the disk remains young. The degree of growth varies, and it remains uncertain how quickly the largest grains appear in all systems and how strongly turbulence opposes settling. From the outside, the disk's appearance depends on how it interacts with light. In scattered light images, small grains in the disk surface reflect starlight and can reveal spirals, gaps, shadows, and warps. In thermal emission at millimeter wavelengths, the disk glows faintly where larger grains in the midplane emit heat. These different windows reveal different layers of the disk. The outer disk is therefore not a uniform environment, but a stratified one where dust size, temperature, and density change with height and radius. What looks like a simple ring at one wavelength can correspond to a more complex structure when viewed in another. The geometry of the outer disk is often flared, meaning the surface rises with radius in a way that allows it to intercept starlight efficiently. A flared shape increases the surface area exposed to radiation, warming the upper layers and enhancing the infrared emission that observers detect. The degree of flaring depends on dust settling, because when dust settles toward the midplane, the surface becomes more transparent and can cool and flatten. Thus, the physical evolution of dust can reshape the disk's overall silhouette. The outer disk is also a region where the interaction between the disk and its environment remains important. If the disk still sits within a remnant envelope, infall can continue at large radii, feeding the disk with fresh material. If the star forms in a cluster with massive neighbors, external ultraviolet radiation can heat and erode the disk's outer layers. This process, photoevaporation driven by external light, can strip gas and dust from the disk's outskirts and truncate its extent. Observations in regions with massive stars show disks with comet-like tails and reduced sizes. In more isolated settings, the outer disk can remain more intact. The degree to which external irradiation shapes disk size and lifetime remains dependent on local environment. In the outer disk, orbital timescales are long. A parcel of gas far from the star takes many hundreds or thousands of years to complete one orbit. This slowness matters because processes such as mixing, drift, and growth proceed over many orbits. The outer disk can preserve gradients and structures for long periods, and it can act as a reservoir that feeds the inner disk slowly. Viscous evolution spreads the disk outward over time while moving mass inward. However, the rate of this evolution depends on how effectively angular momentum is transported. In the outer disk, temperatures and ionization levels are low, which can weaken some magnetic mechanisms. Turbulence may be mild, and transport may be slow. It remains uncertain how uniform the transport is across the outer disk and how it varies between systems, but observations of disk lifetimes and accretion rates suggest that some mechanism persists for millions of years. The chemical environment in the outer disk is dominated by freeze-out and irradiation-driven surface chemistry. In the cold mid-plane, many volatiles are locked into ice mantles. Water ice can be abundant, as can carbon dioxide and carbon monoxide ices depending on temperature. In the warmer surface, molecules can exist in gas form, but ultraviolet radiation can break them apart. This creates a layered chemical structure in which a photodissociation region exists near the surface. Where molecules are fragile, a molecular layer exists below, where shielding allows molecules to survive in gas, and an ice-rich midplane exists below that, where molecules are frozen. This stratification influences what material becomes incorporated into forming bodies. because solids tend to concentrate in the midplane while gas phase chemistry remains more active above. Dust grains in the outer disk carry much of this chemical inventory. Their icy mantles can include simple molecules and more complex organics formed through reactions driven by radiation and cosmic rays. These mantles make grains stickier, increasing the likelihood that collisions result in adhesion rather than bouncing. In cold conditions, the presence of ice can therefore promote growth. Yet growth is limited by the low densities and by the gentle but persistent relative motions stirred by turbulence and differential drift. The outer disk is a place where growth can be slow but steady, and where the earliest steps toward larger solids can be nurtured without immediate destruction by high-speed collisions. Structures in the outer disk can arise from several causes. Pressure bumps can trap dust, creating rings of enhanced emission. Embedded planets or stellar companions can carve gaps. Variations in turbulence or ionization can change how dust concentrates. Snowlines can also create changes in grain properties that affect drift and accumulation. In this region, however, the emphasis remains on the outer environment as a cold, layered reservoir rather than on fully developed planet-building sites. The outer disk holds material, preserves ices, and sets boundary conditions for what moves inward. The outer disk is therefore a quiet frontier of the planet-forming system. It rotates slowly, keeps much of its material cold, and presents a stratified structure where surface layers interact with light, while the midplane remains dark and dense. It is shaped gently by irradiation, by its flared geometry, and by any external environment that may erode its edges. As the inward path continues, the focus shifts from the broad structure of the outer disk to the detailed behavior of gas and dust within it, where the physics of light, motion, and composition becomes measurable in subtler ways. Continuing inward within the disk's outer reaches, the focus narrows from overall structure to the specific behavior of gas and dust as physical materials. The outer disk is dominated by gas, but it is dust that often reveals the disk to observers and that later supplies the solids from which planets assemble. The two components are coupled by drag forces and by shared exposure to radiation, yet they respond differently to gravity, pressure, and heating. Understanding their interaction is central to describing how a disk becomes a birthplace for planets. Gas in the outer disk moves in nearly Keplerian orbits, meaning it travels at speeds set largely by the star's gravity. However, gas pressure adds a small outward force, reducing the required orbital speed slightly below the purely gravitational value. This subtle difference has important consequences for solids. Dust grains, which do not feel gas pressure directly, tend to orbit closer to the Keplerian speed. Because the gas moves a little more slowly, grains experience a headwind. This drag removes angular momentum from the grains, causing them to drift inward over time. In the outer disk, this drift can be slow for tiny grains that are tightly coupled to gas, and faster for pebble-sized grains that feel drag strongly but still retain independent motion. Dust begins as a population of small grains similar to those in the parent cloud. These grains scatter starlight efficiently and dominate the disk's optical appearance. Over time, collisions between grains can lead to sticking. The ability to stick depends on collision speed, grain size, and surface properties. Icy mantles in the cold outer disk can increase adhesion, allowing aggregates to form more readily. Yet sticking is not guaranteed. At higher relative speeds, aggregates can fragment. In an intermediate regime, collisions can result in bouncing, where grains collide but do not adhere or break. The balance between these outcomes shapes the size distribution of solids and influences how much material becomes available in larger forms. The outer disk is a low-density environment compared to the inner regions, so collisions can be infrequent. Still, over many orbits and long times, even rare collisions accumulate. Turbulence provides relative motion, as do differential drift speeds between grains of different sizes. Settling toward the midplane can increase local dust density and therefore increase collision rates. However, turbulence can also stir grains upward, maintaining a population of small particles in the surface layers. Observations in scattered light often show that small grains persist for millions of years, implying that fragmentation or other replenishment processes must maintain them even as some growth proceeds. In the surface layers, dust grains interact directly with radiation. They absorb and scatter light from the protostar, heating and cooling in response. Their temperature sets the thermal emission that telescopes detect in infrared and millimeter wavelengths. In the outer disk, grain temperatures can be only tens of degrees above absolute zero. Yet small differences matter because they control whether ices remain solid. The surface layers can be warmer due to direct irradiation, while the midplane is cooler because it is shielded by overlying dust. The disk therefore contains a cold interior where solids are preserved and a warmer exterior where processing occurs. Gas reveals itself through spectral lines, the specific frequencies at which molecules absorb and emit radiation. In the outer disk, common traces include carbon monoxide and its isotopic variants, along with molecules such as hydrogen cyanide and other species that can survive in certain layers. These lines carry information about temperature and motion. Because the disk rotates, the Doppler shifts of these lines can map velocity patterns, showing how closely the gas follows Keplerian rotation and where deviations occur. Observations indicate that many disks exhibit remarkably orderly rotation on large scales, confirming the basic disk model. At the same time, some disks show signs of winds, inflow, or localized perturbations. The detailed interpretation can be complicated because line emission arises from specific layers, not from the entire vertical column. A central challenge is that the total gas mass is difficult to measure directly. Hydrogen and helium dominate but are often hard to detect in cold conditions. Instead, observers infer gas mass from dust emission and from molecular traces. But these methods require assumptions about dust-to-gas ratio and chemical abundances. Dust can grow and drift, changing its distribution relative to gas, and molecules can freeze out, become photodissociated, or be chemically transformed. For these reasons, estimates of disk gas mass can vary. It remains uncertain how quickly gas is depleted in many disks and how that depletion relates to the growth of solids. The outer disk also contains small-scale structure that affects how gas and dust interact. Pressure variations in the gas can create regions where the headwind felt by dust weakens or reverses. In such a pressure bump, dust drift slows and grains can accumulate. These traps can lead to the formation of rings and arcs in millimeter emission. In some cases, such structures are linked to the gravitational influence of embedded planets, which can perturb the gas and create pressure maxima at gap edges. In other cases, the structures may arise from instabilities in the gas itself, such as variations in viscosity or magnetically driven zonal flows. Observations show many disks with rings and gaps, indicating that dust trapping is common, but it remains uncertain how often planets are the cause and how often disk physics alone produces similar patterns. Within the outer disk, the coupling between gas and dust also influences vertical structure. Gas pressure supports the gas against gravity, giving it a scale height. Dust grains, especially larger ones, tend to settle toward the midplane under gravity. The degree of settling depends on grain size and on turbulence. In a disk with weak turbulence, large grains can form a thin midplane layer with high dust density. In a disk with stronger turbulence, the dust layer remains thicker. This matters because higher midplane dust density increases the likelihood of collective effects, where dust influences gas and dust clumps can form. Even in the outer disk, where densities are low, such collective behavior can become important if dust concentrates enough. The interaction of light and matter in this region is also a story of opacity. Small grains make the disk more opaque at short wavelengths, trapping heat and creating warm surface layers. As grains grow, opacity decreases at those wavelengths, allowing radiation to penetrate deeper and changing the temperature structure. At longer wavelengths, larger grains emit more efficiently, so millimeter observations become sensitive to grain growth. Thus, the disk's observed appearance is not only a tracer of its material content but also a tracer of its evolutionary state. The outer disk is also where the chemical inheritance from the cloud meets disk processing. Some molecules and ices arrive already formed in the parent core and envelope. Others are altered by ultraviolet radiation, by X-rays, and by cosmic rays in disk surface layers. Chemical reactions can create new molecules, while freeze-out preserves others. Observations indicate that disks can host a rich chemistry, including organic molecules. Yet it remains uncertain how representative the observable surface layers are of the midplane where planets form. The midplane is cold and dense and difficult to probe directly, so its composition is inferred indirectly. In this inward step, gas and dust appear as two interwoven fluids with distinct behaviors. Gas carries most of the mass and sets pressure and temperature patterns. Dust carries opacity and the raw solids for planets, drifting, settling, sticking, and fragmenting under the influence of gas drag and turbulence. Their coupling creates both order and complexity, from smooth rotation on large scales to ringed structures that reveal pressure traps. The next inward region continues to follow the solids as chemistry and cold conditions becomes more specific, focusing on how ices and volatiles become stored and transformed in the outer disk's colder layers. Continuing inward within the still cold outer disk, attention settles on the chemistry of ice and the storage of volatile materials. In these regions, temperatures remain low enough that many common molecules do not stay in the gas. Instead, they adhere to dust grain surfaces, building thin, icy mantles. These mantles are not uniform coatings. They form in layers that reflect the thermal and radiation history of the material, and they can trap a mix of molecules in different proportions. This ice chemistry quietly shapes what solids carry inward and what ingredients later become available for atmospheres, oceans, and organic compounds. The formation of ice on grains begins with adsorption, the sticking of gas molecules to a cold surface. When a molecule collides with a grain in a region cold enough, it can lose energy and remain attached. In the outer disk mid-plane, where densities are higher and ultraviolet radiation is weaker, adsorption can be efficient. Over time, a significant fraction of certain volatiles becomes locked into solid form. Water is often the dominant ice by mass in many models, with carbon dioxide, carbon monoxide, methane, ammonia, and other species contributing smaller shares. The exact inventory depends on local temperature, density, and the chemical pathways available. Some ices are inherited from the parent cloud, while others are reformed or altered within the disk. On grain surfaces, molecules are not entirely inert. Atoms and radicals can migrate, especially when occasional heating events or energetic particles provide mobility. Hydrogen atoms, in particular, can move and react readily, turning carbon and oxygen-bearing species into more saturated molecules. In the coldest conditions, reaction rates can still be significant on surfaces because tunneling and surface diffusion allow some reactions that would be slow in the gas. Over time, this leads to the formation of more complex organics in small quantities. Observations indicate that a variety of organic molecules exist in star-forming environments and in some disks, suggesting that surface chemistry can produce meaningful complexity early. It remains uncertain how much of this complexity survives intact into planet-forming regions versus being transformed by later heating and mixing. Ice mantles also evolve under irradiation. Even in shielded regions, cosmic rays penetrate and can generate secondary ultraviolet photons. These photons can break molecular bonds in ice, creating reactive fragments that can recombine into new molecules. This process can increase chemical diversity and can create radicals that remain trapped until the ice warms. When warming occurs later, these radicals can react rapidly, producing bursts of chemical activity. Such pathways are considered important for forming certain complex molecules, though the relative importance of different radiation sources remains an area of active study. The outer disk surface differs from the midplane. In the surface layers, ultraviolet radiation from the central protostar and from the broader environment is stronger. There, molecules can be photodissociated and ices can be eroded. The surface chemistry therefore favors simpler molecules and ions, with a continual cycle of formation and destruction. Between the surface and the midplane lies a molecular layer where shielding is sufficient for molecules to survive in gas form, but temperatures can still be low enough for some freeze-out. This layered structure means that the same species can exist in different phases at different heights, and that vertical mixing can exchange material between layers. Vertical mixing, driven by turbulence, can lift icy grains from the midplane into warmer or more irradiated layers, and then allow them to settle back down. This circulation can expose ices to radiation, altering them chemically, and then return processed solids to the midplane where they can join the planet-forming reservoir. The efficiency of this mixing depends on the strength of turbulence, which varies across disks. It remains uncertain how strongly turbulence mixes the midplane in all systems, but observations of certain chemical traces suggest that some level of mixing is common. Ice mantles influence physical growth as well as chemistry. Icy surfaces can increase the stickiness of grains, making it easier for collisions to lead to adhesion. In cold regions, this can help grains grow from micron sizes to larger aggregates. The growth, however, is still limited by relative velocities and by the structure of aggregates. Fluffy, porous aggregates can form, which have a large surface area and interact strongly with gas. Such aggregates can grow by gentle collisions but can compact or fragment if collision speeds rise. The interplay of stickiness and fragility shapes the size distribution of solids and affects how readily material can concentrate into dense midplane layers. Volatiles stored in ice also influence the distribution of mass between gas and solids. In cold regions where carbon monoxide and other abundant volatiles freeze out, the gas phase abundance of these species drops. This alters cooling rates and can change the ionization balance because some molecules are key participants in chemical networks that produce ions. It also affects observational traces. Carbon monoxide is often used to infer gas mass and temperature, but if it is depleted by freeze-out, its emission no longer provides a straightforward measure. This leads to uncertainties in interpreting disk observations. The presence of freeze-out is well supported, yet the degree to which it depletes carbon monoxide in different disks remains uncertain. The storage of volatiles in ice is not permanent. It depends on temperature. As the inward path continues, temperatures slowly rise, and certain ices become unstable. However, even within the outer disk, temperature is not uniform. Local heating can occur in shocks, wherein falling material meets the disk, or in spiral structures where density waves compress gas. These local events can cause transient warming that partially sublimates ice, releasing molecules into the gas. When the region cools again, molecules can refreeze, sometimes in different proportions or trapping different species within the ice. Such cycles can alter the composition of the ice mantles over time, even without a large-scale change in radius. Grain surfaces can also trap gases in a process sometimes described as clathration or as physical trapping in porous ice. In certain temperature ranges, water ice can capture other molecules within its structure, allowing some volatiles to remain solid at temperatures where they might otherwise sublimate. The details depend on pressure, temperature, and ice structure. While such trapping is plausible and supported in laboratory studies, it remains uncertain how efficiently it operates in real disks and how much it alters the volatile inventory carried inward. In the outer disk midplane, the overall effect is a quiet sequestration. Volatiles become part of solids. Chemistry proceeds slowly on surfaces, guided by faint radiation and by rare energetic events. The disk stores its most mobile ingredients in a stable form, preserving them against immediate loss. This stored inventory sets the stage for later transitions as the inward path approaches zones where temperature boundaries become decisive. The next inward region focuses on those boundaries, where specific ices begin to turn back into gas, reshaping both the composition of solids and the behavior of drifting grains. Continuing inward, the disk's cold chemistry begins to intersect with a steady rise in temperature. The gradual warming is not uniform, and it does not create a single boundary. Instead, different molecules transition from solid ice to gas at different characteristic temperatures. The locations where this happens form a set of radial zones often described as snow lines. Each snow line marks a change in what solids are made of and how much solid material is available to build larger bodies. In the disk, these transitions are quiet but consequential, because they alter stickiness, opacity, and the distribution of mass between solid and gas. In the outermost cold midplane, many volatiles remain frozen, moving inward by tens of astronomical units. Carbon monoxide ice becomes less stable and begins to sublimate where the midplane reaches slightly warmer temperatures. Farther inward, carbon dioxide transitions, and closer still, water ice becomes unstable. The specific radii depend on the luminosity of the central star, the disk's density and opacity, and the balance between irradiation and internal heating. Because young stars vary in luminosity and disks evolve over time, snowline positions are not fixed. They can shift inward or outward as accretion rates change and as dust settling alters how heat is trapped. The transition at a snowline changes the local supply of solids. Beyond a snowline, a volatile contributes to solid mass in the form of ice. Inside it, that volatile exists mainly as gas, reducing solid mass. Water is especially important because it can be a large fraction of the solid inventory in cold regions. Beyond the water snowline, grains are coated with water ice, increasing total solid surface density and often increasing sticking efficiency. Inside the water snowline, grains lose that ice and become more refractory, composed mainly of silicates and other high-temperature materials. This shift can change how easily grains grow, how they fragment, and how they drift. Snowlines also influence gas composition. When an ice sublimates, it releases molecules into the gas phase. This locally increases the abundance of that species in gas, which can alter cooling rates and chemical reactions. Gas phase water and carbon-bearing molecules can participate in reactions driven by ultraviolet radiation and by ionization. Producing other species. The redistribution between ice and gas is not purely local, because gas and small grains can diffuse. Vapor released inside a snowline can move outward by diffusion or turbulent mixing, and then recondense just beyond the snowline, a process that can concentrate solids in a narrow region. Over time, this cycle can enhance the density of ice-coated grains immediately outside a snowline. This concentration effect depends on transport. If turbulence is strong enough, it can spread vapor and blur the boundary. If turbulence is weak, the recondensation zone can remain narrow and sharp. Observations indicate that some disks show ring-like enhancements in dust near expected snowline locations, suggesting that snowlines can contribute to dust trapping and ring formation. However, it remains uncertain how often snowlines are the dominant cause of observed rings, since planets and other instabilities can create similar structures. The physical properties of grains change at snowlines. Ice-coated grains can be more adhesive and can have different surface energies than bare grains. This affects the threshold collision speeds that lead to sticking versus bouncing or fragmentation. Beyond the water snowline, icy grains may stick more readily, allowing growth to larger sizes before fragmentation becomes dominant. Inside it, growth can be more difficult because silicate grains tend to be less sticky at low collision speeds. This difference has been proposed as one reason why giant planet cores may form efficiently beyond the water snowline, where solid mass is higher and growth may be easier. Yet the details remain uncertain because laboratory results, aggregate structure, and disk turbulence all influence collision outcomes. Snowlines also change the disk's opacity and therefore its temperature structure. When grains lose ice, their composition changes, and their size distribution can change as well. The abundance of small grains affects how the disk absorbs and emits radiation. A region where grains grow rapidly and settle can become more transparent in the surface layers, allowing deeper penetration of starlight, while the midplane can cool if less heat is trapped. Conversely, a region with abundant small grains can remain more opaque and warm in its surface layers. Because snow lines can influence growth, they can indirectly influence temperature, creating feedback loops where temperature affects ice stability and ice stability affects growth and opacity. The snowline concept is simple in outline, but real disks are three-dimensional. Snowlines are not perfect circles. They can vary with height because the surface layers are warmer than the midplane. A volatile might be gaseous in the surface while still frozen in the midplane at the same radius. This creates a snow surface rather than a single line, with complex shapes depending on heating and shielding. Observations often probe surface layers, so they may detect gas phase molecules at radii where the midplane remains icy. This complicates interpretation and contributes to uncertainties about midplane conditions, where planet formation is most active. Time variability adds another layer. If accretion onto the star increases temporarily, luminosity rises and snow lines move outward. During such a warm phase, ices can sublimate over a wider region. When luminosity declines, snow lines retreat inward and material refreezes. This cycle can change the distribution of volatiles, potentially moving water and other species into new zones and altering the composition of solids that drift inward. Observations of some young stars indicate past heating events through chemical signatures, though it remains uncertain how widespread such chemical memories are. Snowlines also intersect with dust drift. Pebble-sized solids drift inward through the disk because of the gas headwind. As pebbles cross a snowline, the ices they carry can sublimate. This can reduce pebble mass and change their aerodynamic properties. The released vapor can either accrete inward with gas or diffuse outward and recondense. the remaining refractory core of a pebble can continue inward, supplying rock-rich material to inner regions. Thus, snowlines act as filters that strip volatiles from drifting solids, separating the pathways of water and rock. This filtering is central to understanding why inner rocky planets are often dry compared to outer bodies, though it remains uncertain how efficient the separation is in every system and how much mixing later blurs the gradient. In this inward region, the disk's cold storehouse begins to transform into a set of zones defined by temperature thresholds. Ices do not vanish everywhere at once. They retreat in sequence, reshaping both the solid inventory and the gas chemistry. These transitions create opportunities for dust concentration just beyond snowlines, and for changes in how grains grow and drift. The next inward region follows the solids more closely as they respond dynamically to these changes, focusing on how dust settles, aggregates, and migrates toward the midplane and inward, forming the population of pebbles that becomes the immediate feedstock for larger bodies. Continuing inward, the disk remains cool enough for much of its mass to stay in molecular form, yet the focus shifts from chemical boundaries to the physical pathways by which solids reorganize. Dust grains do not remain suspended forever in the same vertical layer where they begin. Under the star's gravity, solids tend to settle toward the midplane, the densest plane of the disk. At the same time, collisions cause grains to grow into aggregates, and gas drag causes these aggregates to drift inward. This region is defined by the slow convergence of many small solids into a thinner layer and into larger sizes, creating the pebble population that bridges microscopic dust and macroscopic bodies. Settling begins because gas is supported by pressure while dust is not. Gas forms a thick layer with a characteristic scale height set by temperature and gravity. Dust grains feel the star's vertical gravity and would fall toward the midplane if there were no gas. But gas drag resist their motion. Small grains, with little inertia and a large surface area relative to their mass, remain tightly coupled to gas and settle very slowly. Larger grains and aggregates decouple more and can settle faster. The rate depends on the stopping time, the time it takes for a grain's motion relative to gas to be damped by drag. In the outer and middle disk, where gas density is lower, stopping times can become longer for the same grain size, making grains more responsive to gravity and more able to settle. Turbulence competes with settling. Turbulent gas motions stir dust upward and mix it vertically. The balance between downward settling and upward stirring determines the thickness of the dust layer. If turbulence is weak, larger grains concentrate into a thin midplane band. If turbulence is stronger, grains remain more spread out. Observations suggest that many disks show evidence of vertical stratification, with large grains concentrated closer to the midplane and small grains still abundant in the surface layers. The exact strength of turbulence in different disks remains uncertain, but the pattern of settling appears common. As dust settles, the local dust-to-gas ratio in the midplane increases. Even if the overall disk remains gas-rich, the midplane can become a region where solids are relatively concentrated. This concentration matters because it increases collision rates and encourages collective behavior. Grains in a denser layer collide more often. They also influence the gas more strongly through drag, which can lead to feedback effects. In the outer disk, the beginning of such concentration sets the stage for later instabilities that can create planetesimals, though in this region the focus remains on the gradual build-up rather than the final collapse. Growth from grains to pebbles proceeds through collisions. Initially, micron-sized grains collide gently and can stick by surface forces, especially when icy mantles make surfaces more adhesive. These collisions form fluffy aggregates, porous clusters with many voids. Porosity affects how an aggregate interacts with gas. Fluffy aggregates have a large cross-section for their mass, making them well coupled to gas and slowing their drift. As aggregates grow, collisions can compress them, reducing porosity and increasing density. The balance between growth and compaction depends on collision energies and on the mechanical strength of the aggregate. Laboratory experiments and models indicate that aggregates can follow different growth paths, sometimes remaining porous and sometimes becoming more compact. It remains uncertain which path dominates in different regions of disks, and how this affects the timing of planetesimal formation. As aggregates reach pebble sizes, their interaction with gas changes. Pebbles experience a significant headwind because gas orbits slightly more slowly than Keplerian speed. This headwind removes angular momentum and causes inward drift. The drift speed depends on pebble size and on local gas pressure gradient. There is a size range for which drift is fastest, often around pebble to small boulder sizes depending on disk conditions. This creates a bottleneck in growth because pebbles can drift inward toward the star before they grow into larger bodies that drift more slowly. This challenge is sometimes described as a drift barrier, and it is one of the central problems of planet formation theory. Drift is not simply a loss, it also transports solid material inward, supplying the inner disk with mass. Pebbles formed in colder outer regions can drift toward warmer zones, carrying ices and refractory materials. As they move, they can cross snow lines and lose volatile components, leaving behind more refractory cores and releasing vapor that can diffuse and recondense. Drift, therefore, couples the disk's chemistry and its solid dynamics. The midplane becomes a conveyor belt where solids are constantly reshaped by temperature and by drag. Not all regions allow free drift. Pressure bumps and traps can slow or halt pebble migration. A local maximum in gas pressure reduces the headwind felt by solids. At the pressure peak, gas can orbit at nearly Keplerian speed, and drift can stop. Pebbles then accumulate. Such traps can form at the edges of gaps, at snowline-related transitions, or through disk instabilities that create long-lived zonal flows. Observations of rings and asymmetries in disks suggest that dust trapping is widespread. In this region, the key point is that settling and growth do not inevitably lead to rapid inward loss, because disk structure can provide places where pebbles gather and persist. The midplane environment also influences collision outcomes. Relative velocities between pebbles arise from turbulence, from differential drift, and from settling itself. If turbulence is weak, relative velocities can remain low, favoring sticking and gentle growth. If turbulence is stronger, collisions can be energetic enough to fragment aggregates, replenishing small grains and slowing net growth. Fragmentation produces a steady supply of fine dust that can be lofted into surface layers, maintaining opacity and affecting disk heating. This recycling links the midplane to the surface. Even as pebbles settle and grow, fragmentation can keep the disk's upper layers dusty and reflective. Pebble formation is therefore not a single step, but a dynamic balance. Some solids grow and drift inward, some are trapped and concentrate, and some fragment and return to smaller sizes. The relative importance of each pathway depends on disk properties such as surface density, temperature, turbulence, and the presence of pressure structures. It also depends on time, because the disk evolves. Gas slowly accretes onto the star and may be lost to winds, reducing density. As gas density declines, stopping times increase for the same pebble sizes, changing drift rates and settling behavior. Over millions of years, the disk can become more favorable for some processes and less for others. In this inward region, the picture becomes more kinetic and more specific. Solids are no longer merely passive tracers of light. They are a population with trajectories, collisions, and changing internal structures. They settle into a denser midplane, grow into pebbles, and begin to migrate inward under the influence of gas drag. The midplane dust layer becomes a crucial arena, because increasing solid concentration there sets the conditions for the next inward step, where concentration can become strong enough that collective instabilities and gravity begin to convert pebbles into the first kilometre-scale bodies. Continuing inward, the disk's midplane is no longer viewed as a smooth, uniform sheet. The closer look reveals that many disks develop pronounced substructure, patterns that appear as rings, gaps, arcs, and spirals. These features are not merely decoration. They are the physical expression of how gas pressure, dust drift, and disk evolution interact. In this region, the disk becomes a patterned environment where solids are guided and sorted into preferred locations, and where the earliest planet building zones may be marked by persistent concentrations of material. The most widely observed forms of substructure are rings and gaps. In millimetre wavelength images, rings appear as bright bands where larger grains are concentrated, while gaps appear as darker lanes where dust is depleted. The brightness does not directly measure total mass, because emission depends on temperature, grain size, and opacity. Still, the prevalence of ringed disks indicates that dust is often organized into narrow radial zones. This organization suggests that simple inward drift is frequently interrupted. Instead, dust is trapped, held in place by changes in the gas pressure profile. A pressure trap forms where the radial gradient of gas pressure creates a local maximum. In most disks, gas pressure decreases outward, producing the headwind that drives dust inward. If a region develops a local pressure peak, the headwind weakens as solids approach it and can vanish at the peak. Dust then piles up. Such pressure maxima can arise in several ways. A growing planet can perturb the gas, carving a gap and creating pressure maxima at the gap edges. Variations in disk viscosity can create transitions in accretion flow that lead to pressure bumps. Magnetically influenced regions can produce zonal flows, long-lived bands of slightly different pressure. Snowlines can change ionization and grain properties, which can alter turbulence and create subtle pressure features. In many systems, more than one of these mechanisms may operate, and distinguishing among them remains challenging. When a planet is the cause, the physics involves gravitational interaction between the planet and the disk. The planet launches spiral waves in the gas. These waves carry angular momentum and can steepen into shocks, redistributing gas and opening a gap if the planet is massive enough, and if disk viscosity does not quickly refill the region. Even a lower mass planet can create partial gaps or weak pressure perturbations that trap dust more effectively than they trap gas. This is because dust responds strongly to pressure gradients. Thus, a disk can show sharp dust rings even when the gas gap is modest. Observations indicate that some disks show kinematic signatures consistent with embedded planets, yet it remains uncertain how many rings are caused by planets and how many arise from disk-intrinsic processes. When disk-intrinsic processes produce rings, one candidate involves changes in how turbulence transports angular momentum. If viscosity varies with radius, the accretion flow can create zones of accumulation. Another candidate involves magnetically driven zonal flows that create long-lived bands of slightly higher pressure. These flows can arise from the interaction of magnetic fields and rotation, even when the gas is only partially ionized. In addition, instabilities at sharp transitions in density or temperature can create vortices, swirling regions that trap dust into arcs or lopsided clumps. Such asymmetries are observed in some disks, suggesting that vortices can form and persist. It remains uncertain how stable these structures are over long periods and how often they lead directly to planetesimal formation. Rings and gaps influence not only where solids collect but also how they evolve. A ring with enhanced dust density increases collision rates and can accelerate growth from pebbles toward larger aggregates. It also raises the dust-to-gas ratio locally, making collective instabilities more likely. In a gap, reduced dust can lower opacity, allowing deeper penetration of starlight and altering local temperature structure. This can change chemistry and gas scale height, feeding back into pressure structure. Thus, substructure is not merely a passive imprint, it can actively shape the disk's evolution. Shadows and warps add another dimension. If the inner disk is misaligned relative to the outer disk, it can cast shadows across the disk's surface, creating colder lanes where irradiation is reduced. Such shadows can shift local temperatures and potentially influence snowline positions at certain azimuths. Warps can be caused by companions, by magnetic misalignment between star and disk, or by dynamical effects of forming planets. The presence of shadows indicates that disks are not always flat and symmetric. Their three-dimensional geometry can introduce azimuthal variation, creating regions where the same radius experiences different heating. This adds complexity to the distribution of solids and volatiles. Spiral structures are another common pattern. Spirals can be driven by gravitational instability in massive disks, by tidal interaction with a companion star, or by embedded planets. In a gravitationally unstable disk, spirals arise as the disk's self-gravity competes with pressure and rotation, producing density waves that transport angular momentum. Such spirals can compress gas and dust, creating transient enhancements where grain growth may be favored. Spirals can also induce shocks that heat localized zones, temporarily altering ice stability and chemistry. Whether spirals lead to fragmentation or merely redistribute material depends on cooling and disk mass. Observations show spirals in some disks, but it remains uncertain how often they signal strong self-gravity versus being planet or companion-driven. The presence of substructure also affects how observers interpret disk ages and masses. A disk with rings may have dust concentrated into narrow regions, making parts appear bright and massive while other parts look depleted. The total dust mass might be similar to that of a smoother disk, but distributed differently. This can complicate attempts to infer evolutionary stage from brightness alone. It also affects how gas mass is inferred, because dust influences temperature structure and shielding. Substructure, therefore, is part of the disk's physical reality and part of the observational lens through which the disk is measured. In this inward region, the disk becomes a landscape with lanes and boundaries. Pressure traps, whether planet-induced or intrinsic, act as gathering points for pebbles. Gaps and rings regulate drift, preventing a simple inward sweep of solids. Vortices and asymmetries can concentrate dust into localized arcs. Shadows and warps can create uneven heating. Spirals can compress material and transport angular momentum. The common thread is that solids are being organized into denser configurations, often in narrow zones. This organization is crucial because the next inward step depends on reaching conditions where solids are not merely drifting pebbles, but a collective layer dense enough that new physics emerges, allowing pebbles to clump strongly and begin the transition toward kilometre-scale bodies. Continuing inward, the disk's patterned exterior gives way to the underlying motions that sustain it. Rings and gaps are visible consequences, but beneath them is a constant flow of gas and a constant exchange between layers. The disk is not a static container. It is a rotating fluid that slowly accretes onto the central star while also losing mass and angular momentum through winds. Within it, turbulence mixes material and sets collision speeds for solids. In this region, the emphasis rests on circulation and loss, the mechanisms that determine how long the disk remains gas-rich and how effectively it can reshape solids into larger bodies. Gas in the disk cannot feed the star unless it sheds angular momentum. A parcel of gas in orbit holds too much rotational support to fall inward directly. Over long timescales, angular momentum is transported outward through stresses within the disk. One way to describe this is as an effective viscosity, a measure of how efficiently adjacent rings of gas exchange angular momentum. In reality, the stress can arise from turbulence, from magnetic forces, and from spiral density waves. The result is similar mass drifts inward while angular momentum drifts outward, allowing accretion to proceed. Turbulence is central, but its origin varies across the disk. In regions with sufficient ionization, magnetic fields can couple to the gas and drive instabilities that stir it. These instabilities can create a tangled pattern of motion that transports angular momentum. In regions with low ionization, magnetic coupling weakens and turbulence may be weaker or driven by other mechanisms such as hydrodynamic instabilities. The disk is therefore often imagined as layered, with more active surface layers where ionization from X-rays and ultraviolet radiation is higher, and a calmer midplane where ionization is lower. The degree of layering depends on dust abundance and grain size, because small grains can capture charged particles and reduce ionization. As dust evolves and settles, ionization balance can change, potentially altering turbulence over time. It remains uncertain how strong turbulence is in midplanes of typical disks, and how it varies with radius and age, but observations suggest that at least some disks have relatively low turbulence in their outer regions. Mixing follows from turbulence. Gas motions can transport heat, redistribute chemicals, and move small grains vertically and radially. Vertical mixing can lift icy grains from the midplane into surface layers where radiation processes them, then allow them to settle again. Radial mixing can carry vapor and small solids across temperature boundaries, blurring compositional gradients that might otherwise remain sharp. Yet mixing is not unlimited. If turbulence is weak, stratification can persist. Observations of chemical gradients and of dust settling imply that mixing is present but not always strong enough to erase structure. The disk can therefore maintain both motion and memory, circulating material while still preserving zones. Disk winds introduce another pathway for angular momentum and mass loss. Gas can be lifted from the disk surface and carried away along magnetic field lines, or driven by heating from high-energy radiation. A magnetically driven wind can remove angular momentum efficiently, allowing accretion in the disk without requiring strong internal turbulence. A thermally driven wind, often linked to ultraviolet or X-ray heating, can remove gas from the disk surface, especially at larger radii where gravity is weaker. Both types of winds can coexist. They shape disk evolution by shortening the time during which gas remains available for forming giant planet atmospheres and by changing gas surface density profiles. Winds also interact with chemistry. Gas lifted from the surface carries with it the products of irradiation-driven chemistry and can expose deeper layers by reducing column density. As gas is removed, ultraviolet radiation can penetrate more deeply, altering the balance between molecular and atomic forms. This can shift where certain molecules survive and where ices remain stable. Over long times, winds can therefore contribute to the clearing of the disk from the outside in, though the detailed sequence depends on where mass loss is strongest. The balance between accretion and wind loss sets the disk's lifetime. Observations indicate that many protoplanetary disks persist for a few million years, with a spread that depends on environment and stellar mass. The disk's gas content declines with time, but the rate is uncertain for individual systems because gas mass is hard to measure. Some disks show signs of rapid clearing after a relatively long period of gradual evolution, suggesting a dispersal phase where winds and reduced accretion combine to remove remaining gas quickly. This two-timescale behavior is consistent with models where photoevaporation becomes dominant once accretion rates fall below a threshold. Yet the exact thresholds and the relative roles of different wind mechanisms remain uncertain. Within the disk, these gas motions influence solids directly. Turbulence sets relative velocities between particles, determining whether collisions tend to stick or fragment. If turbulence is stronger, fragmentation is more common, keeping particles smaller and maintaining a supply of fine dust. If turbulence is weaker, particles can grow larger and settle more effectively, increasing mid-plane dust concentration. Winds can remove small grains from surface layers, potentially reducing opacity and changing temperature structure. Accretion flows can carry small dust inward with the gas, while larger pebbles drift relative to gas and respond to pressure structure. In addition to turbulence and winds, there is the subtle influence of diffusion. Even in a disk with modest turbulence, gas and vapor can spread from regions of high concentration to low concentration. Vapor released at a snow line can diffuse outward and recondense, feeding dust enhancements. Chemical species produced in irradiated layers can diffuse downward and be incorporated into ices. These diffusive processes are slow but persistent. They help link distant regions of the disk and can smooth sharp gradients, though they may not erase large-scale compositional differences entirely. The inward path through this region is therefore one of sustained flow. Gas is continually transported and continually lost. The disk is a system in gradual change, with surface layers exposed to radiation and winds, and mid-plane layers more sheltered but still influenced by mixing and accretion. The key outcome is that the disk's gas density and turbulence level are not fixed, they evolve, and this evolution changes the environment in which solids attempt to clump into larger bodies. As the disk ages and as solids concentrate in rings and mid-plane layers, conditions can arise where the dust-to-gas ratio becomes high enough that dust no longer behaves as a passive contaminant. Instead, it begins to influence gas flow strongly, enabling collective instabilities that can rapidly concentrate pebbles into dense clumps. The next inward region focuses on that transition, where the first decisive step toward kilometre-scale bodies becomes possible. Continuing inward, the disk enters a regime where solids can shift from being scattered pebbles to becoming dense clumps. This transition is not simply a matter of individual grains growing larger, it is a collective phenomenon. When pebbles become sufficiently concentrated in the mid-plane, their drag on the gas becomes strong enough to alter gas motion locally. In these circumstances, feedback between gas and solids can create rapid concentration, forming dense filaments and clumps that can collapse under their own gravity into kilometre-scale bodies. These first durable bodies are planetesimals, the foundational building blocks of planets. The starting point is the pebble-rich mid-plane. Settling and drift increase the local dust-to-gas ratio. Pressure traps and rings can raise it further by collecting pebbles into narrow radial zones. As the ratio rises, pebbles no longer behave as test particles moving through a fixed gas background. Their combined drag modifies the gas speed. Normally, gas orbits slightly below the Keplerian speed because of pressure support. This creates the headwind that drives pebble drift. When pebbles are abundant, they partially pull the gas toward Keplerian speed. This reduces the headwind, slowing drift and allowing pebbles to linger. The reduced drift can further increase pebble concentration, strengthening the feedback. One of the leading mechanisms for turning this feedback into strong clumping is often described as the streaming instability. In this process, slight variations in pebble density create slight variations in gas speed. Where pebble density is higher, gas is pulled closer to Keplerian speed, reducing the headwind there. Pebbles drifting from other regions encounter this reduced headwind and slow down, causing them to pile up further. The pile-up creates stronger density contrasts, which enhance the effect. Over time, the system develops narrow, dense streams of pebbles aligned with the direction of orbital motion. Within these streams, local pebble density can become high enough that self-gravity matters. The conditions for strong clumping depend on several parameters. Pebble size matters because it sets how strongly pebbles couple to gas. If pebbles are too small, they remain tightly tied to gas and do not concentrate strongly. If they are too large, they decouple too much and drift differently. A moderate coupling is often most favorable. The local dust-to-gas ratio matters because higher ratios strengthen feedback. The level of turbulence matters because strong turbulence can stir and diffuse clumps, reducing peak densities. Pressure gradients matter because they set the baseline headwind that drives drift and streaming behavior. In many models, pressure bumps that reduce the headwind can help by allowing pebbles to collect long enough for instability to develop. Once dense pebble clumps form, gravity can take over. If the clump's density exceeds a threshold where self-gravity overwhelms internal random motions and tidal shear from the star, the clump can collapse. The collapse can be rapid compared to the slow timescales of grain-by-grain growth. Instead of building kilometre-scale bodies by a long sequence of pairwise collisions, the disk can assemble them in a collective event, turning a large mass of pebbles into a planetesimal population. The resulting planetesimals may be tens to hundreds of kilometres in size, depending on the mass and scale of collapsing regions. This possibility helps address growth barriers such as the drift barrier and the fragmentation barrier, because it bypasses the need to grow gradually through the most problematic size ranges. The internal structure of planetesimals formed this way can reflect their origin. A collapse of pebble clumps can produce bodies that are initially porous, composed of packed aggregates rather than solid rock. Later, heating by radioactive decay and by collisions can compact and differentiate them. In the early stages, however, their properties are governed by the packing of pebbles and by the mixture of ice and rock they contain. In colder regions beyond certain snow lines, planetesimals may incorporate substantial ice. In warmer regions, they may be rockier. Thus, the location of planetesimal formation imprints composition. The timing of planetesimal formation matters as well. If planetesimals form early while gas density is still high, they can interact strongly with gas through aerodynamic drag and through gravitational effects. They can also serve as seeds for rapid growth by accreting pebbles that drift past them. If planetesimals form later when gas density has declined, pebble drift and capture can change, and the window for forming gas-rich planets may be narrower. Observations cannot yet directly time planetesimal formation in most systems, but meteoritic evidence in the solar system suggests that some planetesimals formed very early, within a few million years of the first solids. Whether such early formation is typical remains uncertain, but it indicates that planetesimal formation can occur while disks are still young. The environment that enables streaming-like concentration is often linked to disk substructure. Rings and pressure traps provide natural places for pebbles to accumulate. In a ring, the dust-to-gas ratio can become elevated and the radial drift can be slowed. This creates conditions favorable for collective clumping. Vortices can also concentrate pebbles into localized regions with high density. Spirals can compress solids transiently. Thus, the patterned disk of the previous region becomes the staging ground for the emergence of planetesimals. Even within this framework, uncertainties remain. It is not fully established under which exact disk conditions streaming-like instabilities operate most efficiently, or how sensitive they are to particle size distributions and to turbulence levels. It remains uncertain how often planetesimals form in narrow rings versus more broadly across the disk. It also remains uncertain how the presence of already formed embryos or planets modifies these processes by altering pressure profiles and stirring solids. What is clearer is that purely incremental growth from micron grains to kilometer bodies faces strong barriers, and that collective concentration mechanisms provide a plausible route that aligns with many observations of dust trapping and with the need for rapid early assembly. Once planetesimals exist, the character of the disk's solid population changes. Pebbles remain, drifting and concentrating, but now there are large bodies with their own gravity. These bodies can collide, scatter one another, and accrete more material. They can sweep up pebbles efficiently, especially if relative velocities are moderate, and if gas drag helps pebbles settle into their gravitational influence. The transition from a pebble sea to a planetesimal swarm is therefore a turning point. It creates the seeds from which protoplanets grow, and it shifts the dominant growth mode from collective instability to gravitational accretion. The next inward region follows that new phase, where planetesimals and embryos grow through collisions and through the capture of drifting pebbles, building the first recognizable protoplanets within the disk. Continuing inward, the presence of planetesimals changes the disk from a medium dominated by drag and dust physics into a medium where gravity between solid bodies becomes increasingly important. Planetesimals, once formed, are large enough to survive rapid drift. They move on nearly Keplerian orbits and begin to interact with one another through gravitational stirring and collisions. In regions where planetesimals become numerous, they form a swarm. Within that swarm, a subset can grow faster than the rest, becoming planetary embryos, bodies large enough that their gravity shapes the motion and growth of nearby material. Growth by planetesimal collision proceeds through a combination of geometry and gravity. A larger body presents a larger target, but more importantly, it can gravitationally focus incoming objects, bending their trajectories and increasing the effective cross-section for collision. This gravitational focusing is strongest when relative velocities are low, because the body's gravity has more time to act. In a cold, gently stirred swarm, growth can proceed efficiently as collisions are frequent and tend to merge. In a strongly stirred swarm, relative velocities rise, collisions become more erosive, and growth slows or becomes more complex. The balance between stirring and damping determines whether accretion proceeds smoothly. Gas plays a role in damping. Even though planetesimals are too large to be strongly coupled to gas, smaller bodies and fragments can still be slowed by gas drag, reducing their eccentricities and inclinations. This damping can maintain relatively gentle collision speeds for a time. In addition, as larger embryos grow, their gravitational stirring increases relative velocities, but damping by gas and by dynamical friction, the tendency for larger bodies to be slowed by interactions with many smaller bodies can moderate the excitation. The resulting state can allow a phase of runaway growth, where the largest bodies grow faster and pull ahead, followed by oligarchic growth, where several large embryos dominate their local feeding zones and grow at comparable rates. A second growth pathway becomes important once planetesimals and embryos exist within a disk that still contains abundant pebbles. Pebble accretion refers to the efficient capture of small solids by a larger body. In this process, a pebble drifting through the disk encounters the gravitational field of an embryo. The embryo deflects the pebble, and gas drag dissipates the pebble's relative energy, allowing it to be captured rather than simply slung past. This can be highly efficient because pebbles are small enough that gas drag acts on the timescale of the encounter. The capture cross-section can become much larger than the embryo's physical size, especially when pebbles are moderately coupled to gas. This pathway can allow rapid growth of embryos, potentially building large cores on timescales shorter than those expected from planetesimal collisions alone. The efficiency of pebble accretion depends on pebble flux, the rate at which pebbles drift past a given radius. It also depends on embryo mass, because a body must be large enough for its gravity to capture pebbles in the presence of shear and turbulence. There is a threshold mass for efficient capture, and once an embryo passes it, growth can accelerate. The process also depends on turbulence, because turbulence can stir pebbles out of the embryo's capture region and increase encounter speeds. It depends on the scale height of the pebble layer, which is set by settling and turbulence. A thin pebble layer concentrates pebbles near the midplane and increases capture probability, while a thick layer spreads pebbles vertically and reduces the fraction that passes close to embryos. Pebble accretion also has a natural limit. As an embryo grows, it can perturb the gas enough to create a pressure bump outside its orbit. This bump can halt the inward drift of pebbles, starving the embryo of further pebble supply. This mass scale is sometimes called the pebble isolation mass. When an embryo reaches it, its growth by pebbles slows, and it may shift to growth by collisions with other embryos or by accreting gas if conditions allow. The value of this mass depends on disk properties such as scale height and viscosity. It provides a way to regulate how large solid cores can become in different disk regions. As embryos grow, their gravitational influence extends across a feeding zone, a region of nearby orbits from which they can accrete solids. Within this zone, embryos stir planetesimals and can create gaps in the solid distribution. They can also trap pebbles in resonances or alter drift patterns. In regions with multiple embryos, their feeding zones can overlap. They may compete for pebbles and planetesimals, and their mutual interactions can lead to scattering and orbital rearrangement. During the gas-rich phase, gas can damp some of the excitation, allowing embryos to remain in more orderly configurations. As gas declines, damping weakens, and gravitational interactions can become more chaotic. Collisions between growing bodies can be constructive or destructive depending on speed and geometry. Gentle impacts tend to merge, adding mass. Higher speed impacts can fragment bodies, producing debris that may be reaccreted or lost. The outcome depends on material strength, which differs for icy bodies and rocky bodies, and on internal structure. A porous planetesimal may absorb impact energy differently than a compact one. In regions beyond snow lines, ice-rich bodies can be more prone to certain forms of fragmentation or compaction. Over time, repeated impacts and internal heating can transform bodies, changing their density and strength, which in turn changes collision outcomes. The growth of embryos also generates heat. Accretion releases gravitational energy. Impacts can melt or partially melt material. In addition, short-lived radioactive isotopes can provide internal heating if bodies form early. This heating can drive differentiation, separating metal-rich and rock-rich components, and can drive outgassing of volatiles. These processes are well established in the solar system's early history, as indicated by meteorites and planetary compositions. How common similar early heating and differentiation is in other systems depends on formation timing and composition and remains uncertain. In this region, the disk begins to contain objects that can be described as protoplanets in a physical sense, bodies whose growth and dynamics are dominated by gravity and collisions rather than by simple drag. Their growth pathways can differ. Some may grow primarily by planetesimal collisions, slowly building mass. Others may grow rapidly by pebble accretion, especially if pebble flux is high and trapping structures deliver pebbles efficiently. The relative importance of these pathways is debated, particularly for rocky planets like Earth, where the degree to which pebble accretion contributes remains uncertain. What is clear is that both mechanisms can operate in the same disk at different times and radii. As protoplanets appear, they begin to shape the disk itself. Their gravity can create gaps and rings, reinforcing substructure. They can also interact with the gas and migrate, shifting their orbits over time. Migration can move growing bodies into new environments, altering their access to solids and their eventual composition. The next inward region approaches zones where heat is higher and where rocky materials dominate, focusing on how the inner disk's conditions differ and how those conditions influence the assembly of terrestrial planets and the interaction between solids, gas, and magnetic effects near the star. Continuing inward, the disk enters warmer territory where rock rather than ice defines the solid inventory. The light and heat from the young star are stronger here, and the orbital timescales are shorter. Gas densities are higher than in the outer disk, and the processes that move angular momentum can become more tightly linked to magnetic effects because ionization tends to rise with temperature and irradiation. This inner region is where terrestrial planet building materials dominate, where silicate grains undergo cycles of evaporation and condensation, and where the disk's interaction with the star's magnetic field becomes a central influence on structure and flow. In the inner disk, temperatures can reach levels where the icy mantles that aided sticking in cold regions cannot survive. Water and other volatiles are mainly gas, except perhaps in colder pockets or in brief periods of reduced luminosity. Solids are primarily silicates and other refractory materials that remain stable at higher temperatures. Because the overall solid mass is lower without ice, the surface density of solids can be reduced compared to regions beyond major snow lines. Yet this region is also fed by inward drift of pebbles and by the inward transport of vapor that can recondense under certain conditions. It is a zone where mass supply is dynamic, shaped by the disk's ability to deliver and retain solids. Heating sources in the inner disk include direct irradiation from the star and internal dissipation due to accretion. Where accretion rates are high, viscous heating can warm the midplane substantially, potentially dominating over irradiation in the very inner zones. This creates steep temperature gradients with radius. In addition, the inner disk can be puffed up, forming an inner rim where dust first survives without sublimating. This rim, often located where dust evaporation sets a boundary, can intercept starlight efficiently and cast shadows outward, influencing the illumination of adjacent regions. The rim is not necessarily a sharp wall. It can be rounded and structured, depending on dust properties and gas flow. Silicate grains in the inner disk undergo a cycle driven by temperature. In the hottest zones, some solids evaporate, leaving a region dominated by gas. Slightly farther out, as temperatures drop, vapors condense, forming new grains or coating existing ones. This condensation can create a population of fine dust that affects opacity and can influence growth pathways. Condensation fronts can also create changes in grain stickiness and in the local size distribution, potentially creating zones where solids accumulate or where the mechanical properties of aggregates change. The details of how condensation and evaporation interact with drift and accretion are complex, and it remains uncertain how sharply these fronts structure the inner disk in typical systems. Ionization in the inner disk is enhanced relative to the outer disk. X-rays and ultraviolet radiation from the young star penetrate surface layers, and at sufficiently high temperatures, some alkali metals can become thermally ionized, increasing conductivity. With higher ionization, the gas can couple more strongly to magnetic fields. This coupling can drive magnetically influenced turbulence and can enable magnetic stresses to transport angular momentum efficiently. It also allows for magnetically driven winds launched from inner disk regions, potentially carrying angular momentum away and shaping accretion. The strength and geometry of magnetic fields in the inner disk remain areas of active research, but there is strong evidence that magnetic processes play a significant role near young stars. The star's own magnetic field interacts with the disk at small radii. In many models, the stellar magnetosphere truncates the disk, creating an inner cavity where gas does not orbit in a full disk, but instead flows along magnetic field lines onto the star. This magnetospheric accretion can create hotspots on the stellar surface and contributes to variability. The truncation radius depends on magnetic field strength and on accretion rate. When accretion is stronger, the disk can push closer to the star. When it's weaker, the magnetosphere can hold the disk farther out. This interaction influences the location of the innermost dust and the dynamics of gas close to the star. Within the inner disk, the rapid orbital periods mean that collisions and dynamical interactions occur on faster timescales. Planetesimals and embryos can grow and stir one another quickly. However, the environment can be more hostile to gentle sticking because collision speeds can be higher, and without ice, grain adhesion is reduced. For rocky planet formation, this creates a puzzle similar to the outer disk's growth barriers, but in a different form. Many models suggest that inner rocky planets form primarily from planetesimals and embryos delivered or formed early, rather than by late-stage direct growth from small dust alone. Inward drift of pebbles from outer regions can also supply mass, but as pebbles cross snow lines and lose volatiles, their composition changes, and their ability to contribute to rocky growth depends on how efficiently embryos capture them and whether pressure structures allow pebbles to reach the inner disk. The inner disk is also where chemical gradients become sensitive to even small changes in temperature and irradiation. Gas phase reactions can be rapid, and ultraviolet-driven chemistry can create radicals and ions in surface layers. The midplane remains more shielded but can still be influenced by mixing. The absence of abundant ice in solids changes the volatile content of forming bodies, tending to produce drier compositions unless later delivery occurs. Yet the inner disk can still contain water vapor and other volatiles in gas form, and some of these can be incorporated into solids by adsorption or by the trapping of water in minerals. The degree to which this contributes significant water to rocky planets remains uncertain and depends on disk conditions and timing. Dust evolution continues in the inner disk but follows different rules. Grain growth can be driven by collisions and by condensation of vapor. Fragmentation can be significant because relative velocities can be higher. Fine dust produced by fragmentation can maintain high opacity, affecting heating and the location of evaporation fronts. The inner disk, therefore, can be self-regulating, with dust controlling temperature structure and temperature structure controlling dust survival. In this inward region, the environment becomes more compact, warmer, and more magnetically active. The disk is shaped by an inner rim set by dust sublimation, by strong gradients in temperature and density, and by the coupling between ionized gas and magnetic fields. Solids are predominantly rocky, and subject to cycles of evaporation and condensation. Protoplanets and embryos in this region evolve under faster dynamical timescales, and the disk's magnetic interaction with the star begins to determine how gas flows at the smallest radii. The next inward step approaches the very inner edge of the disk and the process of disk dispersal, focusing on how the disk is cleared and how the planet-forming environment transitions into a young planetary system. Continuing inward to the disk's innermost boundary, the environment becomes defined by a transition between orbiting material and direct accretion onto the star. The inner edge of the disk is not simply the place where matter ends, it is a region where the balance between heat, magnetic forces, and radiation determines how gas and dust survive, where flows can change direction, and where the disk's long evolution begins to close. Beyond this boundary, the disk also faces its final transformation, the dispersal that clears away remaining gas and dust and leaves behind a system of planets, debris, and a young star surrounded by a much thinner remnant. The innermost dust boundary is often set by temperature. Close to the star, dust grains cannot remain solid. They sublimate, turning into vapor. This creates an inner region where the disk may still contain gas but little or no dust. Slightly farther out, at lower temperatures, dust can exist and can form a bright inner rim that intercepts starlight. This rim can be a strong source of infrared emission. Its location depends on stellar luminosity and on accretion heating. It can move inward or outward as the star's brightness changes and as the accretion rate varies. The rim can also be shaped by grain composition, because more refractory grains can survive at higher temperatures than more volatile ones. Inside the dust rim, gas continues inward. Its behavior is strongly influenced by the star's magnetic field. The disk can be truncated where magnetic pressure balances the ram pressure of accretion flow. At this truncation radius, the disk's rotation and the star's magnetic field meet. Gas can be lifted out of the disk plane and guided along magnetic field lines, falling onto the star in funnel flows. Where the gas impacts the stellar surface, it produces localized heating and emission. This accretion is variable, responding to instabilities in the inner disk and to changes in magnetic configuration. The truncation radius is not constant. It shifts with accretion rate and field strength, and this motion can influence the distribution of material near the inner edge. The innermost disk is also a site where winds can be launched. Magnetically driven winds can remove angular momentum and mass from the disk surface. These winds can be coupled to accretion, because removing angular momentum allows gas to move inward. In addition, energetic radiation from the star can heat disk surface layers, driving photoevaporative flows. These thermally driven winds become increasingly important as the disk's accretion rate declines over time. When the supply of material moving inward can no longer replenish what winds remove, clearing accelerates. Disk dispersal occurs through a combination of processes that operate over different radii and times. Accretion steadily removes gas by feeding the star. Winds remove gas by lifting it away. External radiation can erode outer regions in crowded environments, while the star's own ultraviolet and X-ray radiation drives photoevaporation more generally. Over time, the disk's gas surface density declines. As it does, the coupling between gas and solids changes. Pebble drift can slow or speed depending on gas pressure gradients. The ability of gas to damp the orbits of embryos diminishes, making gravitational interactions between planets more chaotic and collision outcomes more energetic. A common picture of dispersal involves the opening of a gap in the gas disk by photoevaporation once accretion becomes weak. In this scenario, winds remove gas most efficiently at certain radii where heating can unbind it. When the wind mass loss rate exceeds the inward accretion supply, a gap forms. The inner disk, no longer resupplied, drains onto the star on a relatively short timescale. The outer disk then becomes more directly exposed to radiation and can be removed from the inside outward. Observations of disks with inner cavities support the idea that clearing can involve an inner hole. However, cavities can also be caused by planets that block dust and gas, and it remains uncertain in many individual systems which mechanism dominates. It also remains uncertain how often dispersal begins with a single gap versus a more gradual thinning across many radii. As gas clears, dust responds in its own way. Small grains can be carried away by winds or can be pushed outward by radiation pressure in some conditions. Larger grains can drift inward and be accreted, or they can remain trapped in pressure bumps that persist even as gas declines. When gas density becomes low, collisions between solids become less damped, and debris generation can increase. The disk can transition from a gas-rich protoplanetary disk to a debris disk dominated by collisions among leftover planetesimals. This transition is gradual in some cases and rapid in others. Observations indicate that many systems move from thick, gas-rich disks to much thinner dusty belts over a few million years, but the exact pathways vary and remain uncertain. In the inner regions, the decline of gas changes planet formation outcomes. If giant planet cores form early enough, they can accrete gas and become gas giants before dispersal. If they form late, gas may be insufficient, and they remain as super-Earths or Neptune-like planets with thinner atmospheres. In terrestrial zones, the removal of gas reduces damping and can lead to a late phase of collisions among embryos, assembling final rocky planets through impacts. The timing of gas dispersal relative to embryo growth therefore influences final architectures. Observations of exoplanet systems show a wide diversity of outcomes, consistent with disks that disperse at different times and with formation processes that proceed at different speeds. As the disk thins, the star's radiation increasingly reaches the midplane. Photoevaporation and photochemistry penetrate deeper. Remaining ices in outer regions can be altered. Inner regions become dust-poor and optically thinner. The system becomes more transparent to observation. The young star emerges in visible light as the envelope and disk clear. Planets that have formed begin to dominate the distribution of mass in solids. Leftover planetesimals remain as belts and reservoirs. Some are scattered into eccentric orbits, later delivering volatiles or creating impacts. Some remain stable in rings, becoming the source of long-term debris. By the end of dispersal, the protoplanetary phase is over. The environment that allowed pebbles to drift, clump, and collapse is largely gone. Gas no longer provides a broad, pressure-supported medium for rapid migration and damping. The disk's patterns, once maintained by fluid dynamics, fade into the gravitational architecture of planets and leftover bodies. The system that began as cold cloud material becomes a star with a surrounding planetary system, shaped by the timing and efficiency of accretion, by the chemistry of ices and rocks, and by the clearing of gas through winds and radiation. What remains is a quieter stage, where the final arrangement continues to evolve through collisions, scattering, and slow dynamical settling long after the disk itself has vanished. The disk has already thinned, and the space around the young star becomes clearer, with far less gas to blur motion or soften collisions. The last filaments of accreting material fade into a quieter pattern of orbits. What remains is no longer a protoplanetary disk in the active sense, but a young system with planets, embryos that may still be merging, and belts of leftover planetesimals that continue to grind and scatter. dust persists as a light haze from collisions, often confined to rings where debris production is steady. The star's radiation travels farther without being absorbed and re-emitted by thick disk layers, and the temperature structure becomes simpler, governed mainly by distance and by the reflective and thermal properties of the remaining bodies. Rocky worlds, if they have formed in the inner regions, continue to be shaped by impacts. Without gas damping, their eccentricities and inclinations can remain excited for a time. Collisions are fewer than in the dense disk era, but they can be more energetic. Some impacts merge bodies, adding mass and changing rotation, some strip mantles or atmospheres, reshaping composition. In outer regions, icy planetesimals can still carry volatiles inward through scattering and impact delivery, but such delivery is irregular and depends on the architecture set earlier. The chemical gradients established by snow lines and by drift are no longer actively maintained by gas flow. They become fossil patterns, modified only by later mixing through gravitational interactions. Giant planets, if present, act as long-term sculptors. Their gravity can clear gaps in planetesimal belts, trap bodies in resonances, and send fragments inward or outward. Smaller planets can also shape debris, creating narrow rings or stirring belts to keep collisions active. The debris itself is a faint echo of the earlier disk, a reminder that planet formation is not a single moment, but an extended transition from fluid dynamics to orbital mechanics. Observations of young stars often show this change as a shift from bright, gas-rich emission to thinner, colder dust rings and occasional gas traces. It remains uncertain how much gas can persist in some systems beyond the main dispersal phase, but the general trend is toward a solids-dominated environment. In the quiet that follows, the system's history is written into the final masses and compositions of its planets and into the location of its remaining belts. The earliest conditions in the molecular cloud, the collapse and disk formation, the chemistry of ice and rock, the concentration of pebbles, and the clearing by winds and radiation all contribute to that outcome. The birth environment recedes into the background, and the planets continue in steady orbits around a star that now shines more freely into surrounding space.